Hey everybody, my name is Ryan and this is my semester project for remote sensing, ENME435. This video is going to walk you through how I designed, built, and deployed my own LiDAR sensor to collect 3D measurements of a real target here on campus, and then process that data into a 3D point cloud. But before I dive into my project, I want to take a second to talk about the technology behind it. Because LiDAR is generally one of the coolest sensing technologies out there, and the chances are it's already part of your daily life without you even realizing it. So LiDAR stands for light detection and ranging, and basically it sends out a pulse of light and waits for it to bounce off something and then come back, and it measures how long that took. And since all light travels 3 times 10 to 8 meters per second, you can then calculate that exact distance to whatever the light hit. And if you do that process thousands of times or even millions of times per second across a wide field of view, you can build an incredibly detailed 3D picture of the world around you, and we'll call that a point cloud. In fact, you actually carry your own LiDAR sensor in your pocket every day with your iPhone, and whenever you open your phone with Face ID, it takes a LiDAR scan of your face to unlock it. So now that you got a little bit of background on LiDAR, let me walk you through how I actually built mine. The setup is mounted to 2 3D printed pieces, which those files can be found on our ELMS canvas page. I then epoxied the two together for a strong, stable hold. The left side of the mount mounts the Raspberry Pi attached to the camera using a mixture of screws, nuts, and zip ties. On the other side is the laser mount, which is held together by an interference fit using a small layer of hot glue and also electrical tape. Once that was put into place, I then attached the 2 wires to the Arduino using hot glue and powered it by a battery pack to produce the laser light. I then attached this whole setup to a standard camera tripod using another customized 3D mount that was provided to us in the ELMS page. And luckily, I was able to find a 1/4-20 nut to secure it to the camera mount. Now all you gotta do is plug in the battery pack and turn the lights off. And here you go. This is the fully set up LiDAR sensor for our project. But now we need to calibrate it. So the process was actually pretty simple for calibrating the sensor. I set the flat target at several known distances using a tape measure, and then I compared those to whatever the sensor reported. And I noticed that up close the accuracy was pretty solid, and at longer ranges is when the error started to grow, which is expected with triangulation LiDAR. The farther away the target, the smaller the pixel shift in the camera image, so small detection errors translate into bigger range errors, which is great up close, but less reliable at a distance. So then on the software side, I tuned my OpenCV thresholds to reliably isolate the laser line from the background noise like sunlight, shadows, or lights from the TV. And once I was confident with the readings, I headed out to measure my target. But the thing about picking your target is that it has to be in a low light environment, and unlucky for us for this project, our campus is pretty safe and it's very well lit. So I had to do some snooping around. Well, what do we have here? This is a Sears cement mixer located in the backyard of the Art and Sociology building. Now, I chose this object because 1, it's located in the dark, but 2, it's surrounded by a wooden fence which blocks out a lot of external light, which I found very useful for actually trying to measure my object. Now, originally I was supposed to measure another object, but it turns out that 1, the object was too big, and 2, there's too much ambient light surrounding it from street lamps or buildings. This picture was taken with my iPhone using night exposure, which tries to take in as much light as possible for taking pictures that you want to see. Now, if I turn that setting off, it would look like this, which shows you just how dark the environment really was. And as you can see with how vibrant the laser is, darkness is super important when you're trying to capture data. like the LiDAR sensor is. So how do we actually capture the data? Well, the laser shines a horizontal line that we will then angle the camera and laser down until we get the bottom of the object. That way it's able to scan the whole thing. Now, this is just a video of showing how the laser would look in one solid smooth motion, but in reality, I scan like this. So when I run my script on my Pi, it'll ask me what the starting degree value is and the end degree value is and what increments of data I want. And so here, I start at angle 0, I end at angle 31, and I measure it in increments of 1 degree. But you might be wondering how I actually measure those angles. Well, on your phone, there's a measure app that tells you exactly what angle you're pointing at. And so using this technology, I was able to tape it to my sensor to get accurate data with my angles. And as a result, I get 31 different images using 31 different angles I've captured with my camera. And then I can turn that into a 3D point cloud, which I will show you how to next. Right now, I'm going to activate Python and I'm going to run my homework 8 data generation script. So this is going to go through all of my front view images saved in my 6 o'clock folder. So here it's going to generate a 3D point cloud, and I mapped a cement mixer so you can see the cylindrical shape. Now all of the additional noise in the back is the wall that was sitting directly behind it. So when I go through my script, I edit what folder I want to take the pictures from and then where I want it, and it'll give me 3 text files. After that, I open up Cloud Compare and I can import them into a 3D mesh like this to show you the final structure. Now that we've ran my code, I'll do that 3 more times to get a text file that looks like this. Now, this is the front view, that's the side view, and then I'm going to import the other side. And there would be a 4th, but there was a wall there, so I wasn't able to measure that part, but it would have been flat anyways. So then I can import all of those text files, orient them in such a way that it represents the real structure, and then just rotate them around to look like this. And so after I get that, what happens? Alright, we upped the point size, and now we're going to do the height ramp again, just so we can see it. Cool. That looks pretty good. Now what's next? Now I need to create normals. Now I need to do my plugin. I gotta click Poisson Recon and output density as SF and hit OK. Oh my goodness, okay. So that doesn't look like it at all. So how can we fix this? So after messing around with the settings, this is the final solid body that I was able to get. Now, I was hoping for more promising results, but overall it was a good experience and definitely a learning curve. And while it doesn't look like how maybe it should be, I definitely think that the next time I do this, it will turn out a lot better. So thank you for watching. Also, note to self, if you're moving buckets in the dark, don't accidentally touch a bucket of acid. Okay, bye.